Aloha guys, and welcome to our first Hanahou video. So in these videos, I will review the concepts that we went over in class that day. So if you need to access the information later from home, you can do so by watching these videos on our website. Okay, so today was our first experience with projectile motion in 2 dimensions. We did our ball toss activity, and we analyzed projectile motion in both the x and the y direction. So recall from class that the arrows that I'm drawing here on the ball can be thought of as representative of the velocity vector of the projectile. And they do a pretty good job of indicating the path that the ball has taken. Now, in order for us to calculate any kind of kinematic equation, we need to look only in the x direction or the y direction. Okay, so only x or y at a time. In order to break apart these green arrows into their x and y components, we need to think about what's happening in the x direction and what's happening in the y direction. Here in the blue, I'll be drawing the x component of our arrow. With the pink, I'll be drawing the y component or the vertical component. Now there were a few great observations that you guys made today in class. One of which was that the x component of this velocity vector does not change. I'll say that again, the x component of our velocity vector does not change. So at each moment in this projectile, the blue arrows remain constant and similar. Now what does change is both the size or magnitude and the direction of the pink arrows or our y components. This you can see illustrated as well when we look at displacement. In the x direction, our displacement continues to increase in the positive direction. On the y-axis, our displacement behaves differently. So you can see here that in the y direction, when we look at displacement, it actually creates the parabolic shape of the projectile. So here on this graph, I've tried to illustrate a resemblance of what you captured today on your video physics application. So in the pink, you see the parabolic shape of the displacement in the y direction, or the vertical axis. And in the blue, you see the displacement in the x direction. If we were to look at this graph and analyze it simply using mathematical tools, you could use our trend for the tangent line to figure out the slope of the YT graph. Looking at the slope of the y displacement and t time graph will give you the velocity. So clearly, this graph here starts with a very steep and positive slope, which starts to decrease, approach zero, get slightly steep and negative, and then very steep and negative. So we would expect that the velocity graph for our y direction would start very positive, pass through zero, and end up very negative, which indeed it does. Okay, so here we're looking at the pink line, which is a resemblance of the velocity in the y direction. Going back to our displacement graph, now looking in the x direction, you can see that there is a constant increase in the displacement in the x direction. With a linear graph for displacement in the x direction, we would expect a constant and horizontal velocity in the x direction, which indeed we did see on video physics. Now the acceleration graph is the change of velocity over time. I'll say that again. The acceleration graph is the change in velocity over time. Since the x direction has a slope of 0, we would say that acceleration in the x direction is 0, or there is no acceleration, which is why our blue velocity vectors up here on our projectile remain the same. Now, in the y direction, our velocity does have a slope that's not equal to 0, and in fact, this is a negative slope. Therefore, our acceleration graph should be constant, horizontal, and negative. Any object in free fall without an applied force, so for example, something flying through the air, something being pushed off a ledge, or even in our ball toss activity, a ball being tossed either just vertically or horizontally also to a partner, should experience an acceleration of 9.8 meters per second towards Earth. So here you can see our graph of gravity. Now hopefully this information is helpful for you guys to answer your ball toss activity questions and start to think about what is happening in these two dimensions. Now for those of you that haven't had trig yet, I don't want you to be intimidated about the math that is going to come when we start to talk more in depth about vectors. Because as you can see here, if this is our projectile, and this is the vector that represents its velocity, we have again our horizontal component and our vertical component. And these two components together create a right triangle. So the velocity vector or the displacement vector or whatever it is that we're calculating that is green or not completely horizontal or completely vertical can be thought of as the hypotenuse of a right triangle. So from here, from our right triangle, we will start to implement more of the trigonometric functions like sine, cosine, and tangent. We haven't quite gotten there yet, so I don't want you to think too much about this, but just know that after we discuss projectile motion in 2 dimensions a little further, we will need to use trigonometry to start accounting for our vectors that aren't perfectly aligned on the x or the y axis. So thanks guys for taking some time to review a little bit. Go forth into your ball toss activity write-up. And if you have any questions, I would love to see you in my office hours, so you're welcome to drop by anytime or book an appointment. Ahui ho.